Welcome to Problem Solving with Miss Jones. I got my picture here, as usual. The first thing we're going to need to do before we dive into anything is find this distance from the negative 2 nanocoulombs to our indicated point, which I'm assuming is in the center of this. So that's 1.5, and that's 1.5. And so because this is a right triangle, I'm going to just use the Pythagorean theorem to find that side. So I'm going to call that side b. So I have c squared equals a squared plus b squared, and when you do that math, you get 2.6 centimeters. So the first question asked us to find the potential at that point. So potential is kq over r, or the distance between them. It might be d in your book. So we can just add these up and we'll leave in the signs there. So here you can see the work for that. Don't forget to convert from nanocoulombs. Nano is times 10 to the negative 9. And don't forget to convert from centimeters into meters. So I'll do one step for you. If we factor out a k, that just leaves you one less thing to type into your calculator. So if we factor out a k here, all that stuff that remains is negative 1.72 times 10 to the negative 7th. And then we just have to multiply that by k, and you get negative 1,544.4 volts. And that's the answer to the first part. Okay, the second part asked about the electric field from all of the charges. So what we're going to have is, remember, the electric field points away from positive charges and towards negative charges. So we have 2 here on the x-axis. The negative 1 is going to be going towards the negative charge, and the positive 1 is going to be going away. So we have 2 electric fields pointing to the left there, and then 1 pointing towards the 2 nanocoulombs at the top there. So we're going to have to break these into x and y and solve for the electric field in the x direction and the electric field in the y direction. So our equation for electric field is E equals kq over r. So I'm going to set up the formula for E in the x direction. So I have here the 2 charges that are in the x direction, the 2 times 10 to the negative 9th over a distance of 0.015, and the 1 times 10 to the negative 9th. Using a little math trick here, again, we can factor out a k and a 0.015. So when you add those together, you get 3 times 10 to the negative 9th. It's just one less thing to type into your calculator. It makes it a little bit easier there. So when you do that math, I got 1,798 newtons per coulomb to the left. So that is in the x direction. And then we just have to do the y direction. So here's the setup for that. One thing I always get asked is why we didn't put in the negative charges where these are negative. And my answer is that we already accounted for the fact that it's negative by making it attracting towards the charge. It's always towards a negative and away from the positive. So when we're doing this, we can use the absolute value. Same with the force equation. When you do F equals K Q1 Q2 over R squared, same type of thing. So when we do this math, I got 691.5 newtons per coulomb upward. So the last thing to do now is just add these together like they're vectors. So we have a component to the left and a component upward, and we need to find the hypotenuse and the angle. So this side is 691.5 and this side is 1798. So when you do the Pythagorean theorem there, you get 1924.4 newtons per coulomb. And then I did the inverse tangent. I'll write that out for you. The tangent of theta equals 691.5 over 1798. That's opposite over adjacent. And when you do that, you get theta equals 21 degrees, and you can say above the negative x-axis, because this would be the negative to the left. All right, and the last question asked about the force on a particle. If we put a particle there, if you're not paying attention, you might want to go back and use this equation, which would be really time-consuming. But you could do it, put that charge there and find all the forces and add them up again. But the good thing about having this electric field is that we know that the force then will equal the electric field times Q. It tells you what force a charge would experience at that point. So all we have to do is take that electric field and multiply it by the 0.5 nanocoulombs, and you get 9.63 times 10 to the negative 7th newtons of force at the same angle, at 21 degrees above the negative x-axis.